So quantum mechanical theory describes the behavior of electrons in atoms. We talked about this a bit in chapter 8, and my general conclusion is that electrons are very squirrely and hard to understand. Right? They can be a wave, they can be a property, we can't know exactly where they are and how fast they're going, etc. But what we do need to just be okay with is that electrons exist in spaces called orbitals. And we can describe for a given atom where the electrons are located using an electron configuration, which hopefully you heard of in your prereq class for this one. So an electron configuration is just a description of the orbitals that are occupied by electrons. So for hydrogen, this is the electron configuration 1s1. So the type of orbital, sp, d, or f, is given as a letter here. The large number before that is the principal quantum number, the principal energy level, and the superscript tells us how many electrons are in that given orbital. So here it's 1. So we talked very generally about Schrodinger's equation in chapter 8, and we can solve that for hydrogen, and solutions show that hydrogen's 1 electron will occupy the lowest energy orbital in the atom. When you get to multi-electron atoms, you can't solve the equation exactly, but approximate solutions show that those orbitals are like the orbitals in hydrogen. The reason we can't solve it is because we've got additional terms that need to be added for electron-electron interactions. Basically, things get very, very complicated. So there's 2 things that happen in multi-electron atoms that are not present in hydrogen, and those are electron spin and energy splitting of sublevels. So we can write electron configurations. Another way to describe where the electrons are is an orbital diagram, and this is a bit more visual. This is the orbital diagram for hydrogen. So here, this 1s orbital is shown as a box, and the electron is shown as a half arrow inside of the box. Remember we talked about the spin quantum number? Spin is a fundamental property of electrons. That quantum number can be +1/2 or -1/2, and we can think of it as like being a top spinning clockwise or counterclockwise, even though that's not exactly what it's doing. Here we're showing in this orbital diagram that this electron is spin up, or +1/2 for its spin quantum number. In a group of hydrogen atoms, about half of the electrons would be spin up and about half would be spin down. And just by convention, when we're drawing these diagrams, we always put the first one in spin up. Any questions? Things are going to be a bit muddly here for a while, and then I think when I talk about my quantum hotel, some of these pieces will fall together, hopefully. So this is kind of like reading the rules for the game. So we mentioned this Pauli exclusion principle in chapter 8 also. No 2 electrons in an atom can have the same 4 quantum numbers. No 2 people can have the same social security number. Right? So each electron has its own set of quantum numbers. If you have 2 electrons that are in the same orbital, 3 of those numbers are going to be identical, n, l, and m sub l. So that means that the 4th one has to be different, and that's that spin. So in the same orbital, one of the electrons will be spin up and one will be spin down. Each orbital can have a maximum of only 2 electrons with opposing spins. And this quantum number business you could think of as being a little bit like an address, right? So think of your place of residence and somebody down the street. So you live in the same city, you live on the same street, right? And in the same state, obviously. So state might be like N, L might be the city, M sub L might be your street, but you have different house numbers, right? And so that's like the M sub S. So most of your address is very similar, but the house number is different. Okay, so that's how it is for electrons. They all have a unique set of numbers. This is true, but I don't think it's worth talking about. So let's talk about helium then. Well, helium has 2 electrons. So the electron configuration for helium would be 1s2. Here's the orbital diagram. So we have 1 electron spin up and 1 spin down. And if we look at the quantum numbers for these 2 electrons, they're both in principal energy level 1. That's the 1 here. They're both in the L equals 0 sublevel, which corresponds to S. And there's only the 1 orbital here, so they both have 0 here, but M sub S for them is different. So this is like state, city, street, and then the house number is different. In hydrogen, the sublevels of each principal energy level have the same energy. And so the orbital energy only depends on what N is. And that's why part of why we can do those calculations using that equation, where we're just looking at what's N, and we can calculate the difference between these 2 energy levels. Because it doesn't matter what sublevel of that energy level the electron is in. We say that orbitals with the same energy are degenerate. In multi-electron atoms, which is like everything but hydrogen, right, the energy of the sublevels gets split. They're not degenerate. And this is caused by charge interactions, by shielding, and by penetration. So in general, we can say within a given principal level, the order of energy is S, P, D, and F. But things get kind of confusing other than that. So I scared somebody last night because it was like, here's Coulomb's law, and they had this like traumatic physics flashback. Okay, this is Coulomb's law, this is a physics thing. We're not going to calculate anything with Coulomb's law, but we're just going to look at how charge and distance affect attraction between electrons, or repulsion between electrons. So the potential energy of 2 charged particles is proportional to their charges divided by the separation. So if we have like charges, say 2 electrons, then this energy is going to be positive, and that's going to be a repulsive energy. If we have opposite charges, positive and negative, then E will be negative, and that means the charges are attracted. The potential energy is going to get bigger as the particles get closer together. And the strength of that interaction will also increase as the size of the charges increases. Okay, so let's just think about a refrigerator. And there's the handles. Here's your refrigerator. And we often use a magnet, right, to hold things, notes and stuff on the refrigerator, right? And so here's your piece of paper, and you've got a magnet on there. So here I'm talking about magnetic charges rather than electrical charges, because we are more familiar with magnetic charges and how they behave, because everybody's played with magnets. They're just kind of fun, aren't they? You know, the magnet just like sticks to the refrigerator, and it doesn't need any glue or tape or anything. You pull it off, it doesn't leave a residue. It's just kind of magical, isn't it? So those are magnetic charges, if you will. There's a magnetic field. And so how strongly that magnet is attracted to your refrigerator depends on how strong the magnet is, and also how far apart the magnet and the refrigerator are. If we put one piece of paper under the magnet, it'll stay up, right? Well, let's add another piece of paper, and another, and another. And at some point, what's going to happen? It's either just going to fall off, or the magnet will stay on there, but the whole thing will start sliding down, right? Because it just can't hold on strongly enough. Well, adding more pieces of paper, we're increasing the distance between the magnet and the refrigerator. And that reduces the strength of the attraction. The other thing that affects how strongly the magnet is attracted to your refrigerator is how strong the magnet is. There are weak magnets, like, you bought a souvenir on a trip at some gas station, and it's probably pretty cheap, and it just barely sticks up there, maybe holds one piece of paper. Then if you get some really cool magnets, like you took apart a hard drive and you took out those magnets, they're super strong, and you stick that on your refrigerator, that'll hold up a whole bunch of pieces of paper. Because it's stronger, because your Q here is larger. So with electrical charges, if the charges are larger, the attraction is larger. If the distance between them is shorter, the attraction is larger. Okay? And that's all we need to know about Coulomb's law. So, in multi-electron atoms, we've got electrons being attracted to the nucleus. Nucleus is positive, electrons are negative. And we have electrons being repelled by other electrons, right? Two negative electrons repel each other. And so the repulsions from those other electrons reduce the attraction of the nucleus. We say the nucleus is shielded by these electrons. And so we can say that the total amount of attraction that an electron feels for the nucleus is called the effective nuclear charge. The closer the electron gets to the nucleus, the more attraction it experiences. So the closer the magnet gets to the refrigerator, the stronger it can hold. And so if we have one of those outer electrons, if it can penetrate into the electron cloud of the inner electrons, it can get closer to the nucleus, and so it will have a stronger attraction. And how far it can penetrate depends on the radial distribution function. So let's talk about shielding first. So here we have a lithium atom. We've got three protons in the nucleus, and we have 3 electrons. So these 2 electrons are in the first energy level, and they're in this s orbital. It's a sphere, right? And then here we have the 3rd electron, and it's in a larger orbital. And so it's farther away from the nucleus. And as it looks at the nucleus, the attractiveness of the nucleus is sort of shielded from it by these electrons here. They're like getting in the way. And so when this looks at the nucleus, it sees positive 3 minus 2. Because these guys are sort of canceling out, they're shielding the charge. Does that make any sense? The nucleus is not as attractive because these other electrons are getting in the way. Okay? If this electron is able to penetrate into this cloud, then it can get closer to the nucleus, so that's an increase. And also now, these other electrons are not in the way. It's right in there with them, and so they're all experiencing the full positive charge of the nucleus. And all of this stuff right now is an explanation of why the energy levels are split. Okay, so I'm not going to test you on that because this is just sort of background information. So we looked at graphs like this very briefly in chapter 8. So here we're looking at the radial probability for different orbitals. And so here's the 1s orbital. Remember, that's a sphere. And it does have a node at 0, but most of it is near the nucleus, right? So it seems like most of it is within about 100 picometers of the nucleus. The 2s orbital is larger, and so the bulk of it is further out than the 1s orbital. But there is a node in the 2s orbital, and so there's this little bump of probability in here, and that's the penetration of the 2s orbital into the 1s orbital. If we look at the 2p orbital, it does not penetrate as much into the 1s orbital. So this 2s orbital, that electron can get in closer to the nucleus and not be as shielded compared to the 2p electrons. And so what this does is it causes the 2s sublevel to have lower energy than the 2p sublevel, because these electrons can get in. So we're looking at larger negative energy, which is lower, right? Going below sea level, going down under the water. So we're looking for a larger negative number. When we get closer to the nucleus, then E will be a larger negative number, and that's more favorable. So that's a lower energy. Any questions? That's one of those things. It's like you probably have a zillion questions, but you don't actually know what they are. Mm-hmm. Right? Yeah.
Wait, so the orbital depends, or the orbital dictates if it's going to, the electrons are in the shield or penetrate it?
Basically, yes. So the 1s orbital could have 2 electrons in it, and so these guys are like buzzing around the nucleus. And so then somebody out here, when it looks at the nucleus, it's all kind of, hazy. You can't see it very well, right? So it's not as attractive. My really weird analogy is you think of a bodybuilder on the beach, right? And they're wearing a bikini or, a bathing suit, very attractive, right? Because just, right, bodybuilder. Well, what if they put on a parka? Or what if they have a whole bunch of people around them, and now you can't really see them? That's actually better than the parka, I think. So they've got these, people just clustered around them. They're all attracted to them, right? Now, if you're on the outside of that group, you cannot see that person as well, and so they're not as attractive to you because you just can't really see them. So that's kind of what the shielding is for the electrons. And then the penetration would be, well, that this 2s orbital kind of squeezes up and pushes into the group of people, and so now it can see the person. Does that make sense?
Yeah.
Yeah. You have to kind of just fix these analogies as I go along. So because of all this business, the sublevels are not degenerate. They're not the same. And in fact, when we get up to the 4th and 5th principle levels, it's so messed up that they're not even, well, you know what? Let's just look at it. So here, principal energy level 1, lowest energy, principal energy level 2, next lowest energy. In the hydrogen atom, the 2s and the 2p would be on the same level. But here, the 2s is lower in energy because its orbital can penetrate into the cloud of the first electrons, and so it's more attracted to the nucleus. The 2p sublevel is not as attractive because it can't do that. Then we go to the 3s, which is higher in energy, and the 3p. And again, these are not degenerate because of that penetration shielding idea, right? And then 3d is higher in energy than p because it's less good at penetrating than the p subshell is. But what's interesting and confusing is that the 4s orbital is actually lower in energy than the 3d orbital. And so we get this weird ordering where we've got 3s and 3p, and then it goes to 4s and 3d, and then it jumps back to 4p, and then 5s and 4d, and it gets all wonky, right? And that's because of the interactions between the electrons in a multi-electron atom. The good news is we don't have to memorize this order. I'm going to show you how it's all hiding on the periodic table. So here's Getting to more principles, Aufbau principle and Hund's rule. So the electrons are going to occupy the orbitals to minimize the energy of the atom, meaning they're going to go into the lowest energy orbital. I decided I'm going to keep track of when the train's coming. That one's at 1:30. The orbitals in the same sublevel, which would be like these guys. So there's 3 p orbitals in the 3p sublevel. These are all the same energy, but these are not the same energy as that one. So the electrons are going to fill in from lowest to highest energy. This is the filling order, but again, we don't need to memorize that. The Pauli exclusion principle tells us that the spins of the electrons within a single orbital have to be opposite. And Hund's rule tells us that when we're filling degenerate orbitals, the electrons will fill them singly first with parallel spins. Like, okay, right. Okay, here it is, the quantum hotel, a discount resort for electrons in Mrs. K's chemistry land. This is this imaginary world in my head, right? So think about a hotel, right? You have different floors in a hotel, first, second, third, right? So those correspond to the principal shells or the principal energy levels. That's the quantum number n. On each floor, there are rooms. The rooms are like the sublevels. In each room, you have beds. The beds are like the orbitals, and people sleep in the beds, and people are like the electrons, okay? Money is like energy, so some of these rooms cost more than others. And these electrons, these people this is a discount resort, these are cheapskates, they're looking for the best deal, right? So they're gonna stay in the rooms that cost the least, okay? So let's kind of look at this. I think this would be, the kind of hotel that you might find in Vegas, right? They have a pyramid. This would be like kind of a half-inverted pyramid. Not really a good building design if you're worried about earthquakes, but there's no earthquakes in chemistry land, right? So here we have, this is the first floor, and this is the second floor, and the third floor, and the fourth floor, and these floors aren't exactly level, and then the fifth floor. On the first floor, there's 1 room. On the second floor, there's 2 rooms. On the third floor, there's 3 rooms. On the fourth floor, there's 4 rooms. So that's what I'm saying here, right? So the floor number is how many rooms are on that floor. And then those rooms, instead of like a normal place where, this room might be 101 and this might be 201 and 202, instead of numbers, we're going to use letters. So on the second floor, there's an S room and a P room. On the third floor, there's S and P and D rooms. On the fourth, there's S, P, D, and unshown would be the F rooms. The S rooms all have 1 bed, so each of these lines is like a bed. All the S rooms just have 1 bed. All the P rooms have 3 beds. The beds are the orbitals. The D rooms have 5 beds. I could have used a hotel like that when we were traveling with 6 children, because some places you have to get 2 hotel rooms because they don't want people sleeping all over the floor. It's kind of a safety hazard, but it just made things expensive. But, have you ever seen a hotel room with 5 beds in it? Yeah, so it doesn't have to really make sense. And then we've got our electrons. And so the electrons are going to come to the hotel and check in for the night. And so the first guy comes in, he wants the cheapest room, right? So the hotel clerk is going to put him in this first room, right? And then another electron comes and also wants the cheapest room possible. Now, normally what people would do is you get your own room, right? But it's going to cost more. And money is really important here. So the second electron is going to share this bed. Now you can kind of imagine that they don't really enjoy doing that, just like you probably don't enjoy the idea of sharing a hotel bed with, somebody you don't know very well, right? So here's the bed, here's the pillows, right? So the first electron that gets here crawls into the bed and, like a normal person, sleeps with their head at the head of the bed, right? The next electron comes in and can't sleep on the floor because the floor is lava, right? Has to sleep in the bed. And so they're going to sleep upside down in the bed. Where did you get that idea from? Trip to Fort Snelling in St. Paul, Minnesota. It's an old fort, and they had, you get to tour it, and they have these bunk beds for the soldiers. And those bunks are super narrow. They're more narrow, they're not even as wide as a twin bed. But 2 soldiers would sleep in there together. Like, what? What was going on there? Well, in the winter, it's like extremely cold, right? Well, if you sleep next to another person, you can share body heat and keep each other warm. If your dog sleeps next to you, that's not so fun in the summer when you're hot. But now when it's getting cooler at night, it feels kind of good. But they would sleep head to toe like this so that they could fit together better in the bunk. Okay? So that's what these electrons are doing. They also want to avoid any, appearance of anything, right? There's nothing going on here, right? So we're going to sleep like this. So we're going to put that electron in there, sleeping in the same bed but upside down. Next electron comes, the cheapest room is full, so he'll have to go in here. And the next electron comes, I'll sleep upside down with that guy. Next electron has to go up into this next most expensive room. Okay, the next electron that comes, is he going to snuggle up with that guy he doesn't know, or is he going to take his own bed? Of course he's going to take his own bed. That's Hund's rule. They're going to occupy these orbitals singly with parallel spins. Okay? Because, the first guy that takes the bed, of course he's going to sleep right side up. It's kind of inconvenient to be upside down. You got to mess around with the covers. So then the next electron that comes in, also going to take a separate bed. The next electron now doesn't have a choice, has to pair up. And then pair up, and that's how the electrons fill in the beds in the hotel. That's how the electrons fill the orbitals in an atom. They're going to take the lower energy orbitals first. If there's 2 of them, they're going to have opposite spins. When you come to one where there's degenerate, these 3 orbitals are degenerate, it's the same energy. This is one room, and say it's $50 to sleep in that room. The price doesn't depend on which bed you take, right? So you could, take any bed. So then they're going to take their own beds because that's not going to cost any extra and it's more desirable. Okay? Any questions? So the electron configuration, you can, yeah.
Can you go back to the model and just show how we know if the orbital is degenerate?
Yeah. So degenerate orbitals means that they have the same energy. So these are 3 beds in the same room. They have the same price, right? These are 3 orbitals in the same sub-level. They're going to have the same energy. This orbital and that orbital are not in the same level. This is on level 4 and that's level 3. They don't have the same energy. The 3s orbital and the 3p orbital are on the same level, but their energies are not the same because of what we were talking about with how the orbitals penetrate into the other orbitals. And that causes this one to be lower in energy than that one. Does that help? And you get to the D room with the 5 beds, and they're all the same energy. All those orbitals are the same energy. And so the electron configuration is like what the hotel clerk might be recording so that he knows which rooms are occupied, right? And so you could write an electron configuration for this, and he might say, well, the 1s room has 2 electrons in it, and the 2s room, that's this guy, 2 electrons, and the 2p room has how many electrons? 6, thank you. And then we've got 3s, so 3s, and that's 2 electrons. And the 3p room has 3 electrons in it. So this is what the electron configuration represents. It's a lot more concise than drawing pictures. And even this is just a very, very basic sketch. I mean, you can't draw, it would be all those weird balloon shapes, right? So it's kind of why I like this hotel analogy is because we can relate some of this bizarre business to something we actually have some experience with. If not personally, at least we've seen TV shows where people stay in hotels, right? So then if we can relate it to real life experience, it can make more sense and be easier to remember. Any other questions? Just want to point out the number of electrons in a neutral atom is equal to the atomic number. So on the periodic table, like carbon is element number 6. Its atomic number is 6. That means it has 6 protons in its nucleus. If the atom is neutral, it also has 6 electrons. So if we need to know how many electrons an atom has, we just need to look at the periodic table, and that will tell us. Each orbital can hold a maximum of 2 electrons, so each bed can hold a maximum of 2 people. The S sublevel is 1 orbital, 1 bed. P sublevel is 3, D is 5, F is 7. These are odd numbers counting by 2. 1, 3, 5, 7. And if you need to know, well, how many electrons could fit in this sublevel, there's 2 in each of the 7 orbitals, 14. So here we have the electron configuration for krypton. It's just a listing of the orbitals with the electrons that are in them as subscripts. So 36 electrons. If we take these superscripts, 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 6, that's going to add up to 36. We've accounted for all of the electrons. That can get a little tedious, and the first part of it's always going to be the same. So what we can do is say, well, here's rubidium with 37 electrons, right? Well, this part is the same as the electron configuration for krypton, right? And so we can shorten this and put krypton in brackets to represent the electron configuration of krypton and just show the extra electrons. This is called a noble gas configuration. And so you can do this by taking the previous noble gas, writing its element symbol in brackets, and then just putting the other electrons into their orbitals. I'm going to practice all of this. So we did hydrogen and helium. Let's look at lithium, beryllium, boron, and carbon. So we're increasing in numbers of electrons. And so here with the orbital diagrams, this is looking more like the hotel to me. So this is a bed and that's a bed. And see, these 3 beds are in the same room. They're all together in a block here. And so, 1, 2, 3, and the next one comes in here, 4, and the next one 5, and the next one 6. And The electron configuration just describes what's going on over here. 1s has 2, 2s has 2, 2p has 2. So let's write the orbital diagram for argon. So the first thing we need to know is how many electrons does argon have? 18. Because element number 18 has 18 protons, it's got 18 electrons. Orbital diagram, this is the boxes. So I'm just going to prepare some beds in the hotel for these guys. So this would be the 1s room. This would be the 2s room and the 2p room. We've got 2 rooms on that floor. This would be 3s and 3p. And then things get a little wonky. We're not going there yet. So we need to put 18 electrons in here. So we're going to go 1, 2, 3, 4, 5, 6. This guy's going to take his own bed because it doesn't cost any extra and it's just a lot nicer. It was 6, 7. Now we got to pair up because we're really, really cheap and we're not willing to spend the extra money to go up to the 3s room. What was that? 6, 7, 8, 9. No, that's 10. 2, 4, 6, 8, 10. I'm at 10. 11, 12, 13, 14, 15, 16, 17, 18. We're just putting electrons to bed. Question? Not quite? Sleep well, my little electrons. So this is the electron diagram, the orbital diagram for argon. Looking at the orbital diagram, we can see if there are any unpaired electrons. Does anybody have their own bed? No, they're all paired up. So we would say there are no unpaired electrons in argon, and that'll become important later. No unpaired electrons. Bless you.